So your checklist where when you're starting a topic, you can kind of look at the information covered here and then kind of check back and see sort of how you're doing on understanding those statements. So kind of getting into our first part of the topic, what is a transition element? Because really before this, we just kind of say, oh, the transition elements, they're the ones in like groups 3 through 12 or the D block, you know, they're kind of in the middle of the table in the short columns. But really there is a specific definition for what something or what makes something a transition element. And it's an atom that has an incomplete D sublevel, or it might have positive ions that have an incomplete D sublevel. And so we're going to focus on the first row, as I mentioned in the D block, so scandium to zinc. And so we're going to talk about why is zinc technically not a transition element, even though it's in the D block. And it has to do with the fact that zinc, it has no unpaired electrons in the D sublevel as an atom or as a positive ion. And that's what makes it not kind of allowed in the transition element group. So if we look, the best way to do this is to compare their electron configurations. So here it gives you the element in this first column. The ion, positive ion, the most common positive ion that they have is in this second one. And then it gives you the electron configuration for both the atom and the ion. So what you'll see here is scandium has an incomplete D sublevel as an atom. Titanium has it as an atom and as an ion. So does vanadium, so does chromium, so does manganese, so does iron, so does cobalt, so does nickel. Copper doesn't have it as a atom, but it does as an ion. Over here, it's only 3D9. It didn't get up to 10. And then if we look at the very end, zinc, it's 3D10 as an atom. It's still 3D10 as an ion. It only loses the 4s electrons. So because both as an atom and as a positive ion, zinc it ends in 3D10. That means its D sublevel is full. And in order to be categorized as a transition element, you have to have an unfilled D orbital as either a neutral atom or as an ion. Okay, so scandium has it as an atom. Copper has it as an ion, and all the other ones have it as both an atom and an ion on this list. And so really these unpaired or unfilled D sublevel, incomplete D sublevel, that's what gives these transition elements a lot of the properties we're going to talk about. It's what allows them to be magnetic. It's what allows them to act as catalysts. It's what allows them to have different colors because of some energy differences. And so all the different things that are going to go in here tie back to the fact that transition elements have incomplete D sublevels. Okay. And so that's why zinc is technically not a transition element. All right, so some physical and chemical properties. We think of transition elements as being kind of the normal metals, you know, like things like copper, silver, gold, platinum, iron, cobalt, zinc. These are the metals that you usually think of if somebody asks you to give an example of a metal, because they're used for things like jewelry, coins, building materials, okay? They have all these properties, high electrical and thermal conductivity, so we can use them for like pots and pans for cooking because they conduct heat really well. The high electrical combined with being ductile, we use copper as like copper wire for how your house has electricity running through it. It's copper wire that's in the walls of your house or your apartment. And that conducts electricity, and it's also very malleable and ductile. It can be drawn into these thin wires. They all have pretty high melting points. If you've ever used, you know, like a cast iron skillet, like I have a cast iron skillet that it was my grandmother's that like I've inherited it, and so it's pretty old, but it conducts heat really well, and it has a pretty high melting point, and so it's actually really good to cook in. And you can also stick it straight in the oven. A lot of modern pots and pans, if the handle has got any plastic on it, you can't put that in an oven. And so with something like that's like a cast iron skillet, the whole pot, handle, everything is all made of iron. And so you can bake it in the oven with it. You can cook it on the stove. It's, you know, it's really nice because it conducts the heat very well and it distributes heat evenly when you cook. Malleability, so they can be beaten into shape. So you can flatten them out into thin sheets. So pretty much all of them have this. And malleable also meaning like, you know, that's how we can make coins and jewelry out of them because they can be shaped into different forms. High tensile strength, that means they can withstand a lot of weight or a lot of force. So that's why you see them used to like copper is used for pipes. You see them used in building materials and things like that. And then the last one is that there are 3 specific ones, iron, cobalt, and nickel, that are ferromagnetic. The other ones, they aren't necessarily going to be magnetic, okay? Just because something's a metal doesn't mean it's magnetic. It has to do with these d sublevel electrons. So some chemical properties that they have. They form compounds with more than one oxidation number. So like, you know, they can be +2 or +3 or +4 or on and on. All of them form positive ions because they're all metals. As we're going to talk about next time, they can actually also form colored compounds. They form different colors. And again, it goes back to, it has to do with the fact that they have those incomplete D sublevels. And that sort of plays into why they can form different color compounds. And then they can also act as catalysts. They can speed up reactions, as I mentioned a little earlier. So complex ions, they can form these complex ions when you dissolve these metals ions in solutions. They can bond to the water molecules, or if there's something else in the solution, like if there's chloride ions or cyanide ions or something, they can bond to those ions as well. And they make these complex ions when they do that, okay? And a complex ion, it consists of a central metal ion. In this case, that would be the iron in this picture. And then it's also bonded to ligands. In this picture, the ligands are these 6 water molecules. All of these are water molecules. The only reason these 2 over here, the formula looks different, is because they're drawing it to show you that it's actually the oxygen that is bonded to the iron atom. So it's still H2O. They just wrote it differently to show what's doing the actual bonding, and it's the oxygen. And the reason that the oxygen is doing the bonding is because iron is just by itself, it's just iron. It doesn't have any extra electrons once it's become an ion. And so what happens is, in order for these ligands to bond to the central metal ion, they use their lone pairs of electrons and they form what's called a coordinate covalent bond. A coordinate covalent bond is a covalent bond where both of the electrons being shared come from the same substance. They come from the same molecule. So in this case, the water is donating 2 electrons from the oxygen to pair up with the iron. The iron is not donating any electrons. A normal covalent bond, one electron would come from one atom and 1 electron would come from the other one, and they would share that pair that way. But in a coordinate covalent bond, both of the electrons being shared come from the same molecule or the same atom, okay? So that's what makes this unique, is it's a coordinate covalent bond. And in this case, there are 6 of them, and they're all bonding to the iron. So you can see this kind of has this weird name, but it's hexa because there are 6 of them. It's aqua because they're water molecules like aqua. And it's iron because that's the central metal ion. And it's iron 3 because that's the charge, okay? So hexa aqua iron 3 ion is sort of how this would be named. And so in this one, once I can look at the ligands, I can figure out what's called the coordination number. The coordination number is the number of those coordinate covalent bonds between the ligands and the central metal ion. So in this one, it says there's 6, because as I told you guys, there's 6 water molecules that we can see here that are bonded, and they all are bonded by a coordinate covalent bond. So this one would have a coordination number of 6. And then from the coordination number, you can actually figure out the shape of the ion. So if something has 6, like our example with the water molecules, or like this one, those are going to be octahedral because they're bonded to 6 different things. Now this goes back to like topic 4 with bonding. And we have not gotten to the HL of topic 4 yet, where we learn like octahedral shapes. But anything that has 6 bonds like that, it's going to be octahedral. If it's got 4, like the second one on here, that could be tetrahedral, because remember, anything with 4 bonds is tetrahedral. It could be square planar if there's also lone pairs on the central atom, but in this picture, it doesn't look like there are. So I would guess that this one is going to be tetrahedral because of that. And then if there's 2 of them, obviously like the one on the right, that one's going to be linear. All right, so the ligands are what those things with the lone pairs are that cause that coordinate covalent bond to happen to form the complex ion. So the next section really, it just kind of goes into a little bit of detail about ligands, what they are, what are some examples of them. So they're the species with lone pairs of electrons that form coordinate covalent bonds with a central metal ion. These are your most common ones. There's more that we'll talk about later next time, but these are the most common ones. You need to be aware of them and know which ones are neutral and which ones have a negative charge, okay? Because that's going to affect how we figure out some charge things here in a little bit, okay? As I mentioned, they use their lone pairs of electrons to form coordinate covalent bonds. If I were to draw out the Lewis structure for all 5 of these things, you would see that all of them have at least 1 lone pair of electrons on their central atom. So water actually has 2 pairs of electrons on top of its oxygen. Cyanide, that's CN, it's C triple bonded to an N. And then it has a lone pair here. And then it's got a negative charge. Chloride, that's just Cl. It's going to have all 8 dots around it because it's got a -1 charge. NH3 is ammonia. So it would look like this, an N with 3 H's bonded, but then it has a lone pair on the nitrogen in the central atom. And then CO is carbon monoxide. So it's carbon, it's triple bonded to O. Whoops. Uh-oh. And then it also has some lone pairs on here. So what they have in common is that they all have extra lone pairs that they're willing to like donate to make that coordinate covalent bond. Okay. There is a special kind of ligand called a polydentate ligand. And it has more than 1 lone pair of electrons that can form a coordinate covalent bond. And it sort of acts like kind of like one of those claws, like on that you see at like the little games at like arcades. If you look, what's happening on this picture is that this oxygen, this oxygen, this oxygen, this oxygen, and these 2 nitrogens, all of them have a lone pair on them. And so there's 6 different lone pairs all on that one molecule. And what happens is all 6 of them will attract the central metal ion, which is just being represented by an M here. And all 6 of them will make that complex ion. And so it's kind of like it's surrounding it from all sides. So instead of just an individual molecule bonding to each side of the central metal ion, all 6 of them are already on this other bigger species, this other bigger molecule. And so a big example of this is this thing called EDTA with a 4- charge. And it's the reason it's common is because, as it says here, this last part, it's a food additive. And so what they do is they'll put it into, companies will add it to their foods or to their product. And what it does is it removes metal ions from the solution and inhibits an enzyme reaction from happening. Okay, so the stuff that was actually for today, the first part, this is pretty easy, just deducing the charge on the central metal ion. If this is where you got to pay attention to the charge on your ligand, okay? So as I was just saying up here, like water and ammonia and carbon monoxide are all neutral. Cyanide and chloride have a -1 charge, and that's important because when you're trying to figure out the charge on the central metal ion, it may or may not be the same as the whole complex ion. So on this one, it's a +3 on, or 3+ on the entire complex ion. And I want to know, well, what's just the charge on the Fe right here? Is it 3+ or is it something else? That's where I have to go around and I have to look at all of the ligands that it's bonded to. And do any of them have a charge or are all of them neutral? On this one, all 6 of them are water molecules. And so all 6 of them are neutral. And if all of your ligands are neutral, then that means that your central metal ion has the same charge as the whole complex ion. If they are not all neutral, like for example on this one, I have a 3- charge, but all 6 of my ligands, they're all cyanide ions. They're all Cn, and Cn, if we look back up on that list for the ligands, Cn has a -1 charge. Okay, so if that happens, I have to do a little bit of math. I have to take my charge, which on this one the charge was, it's 3- or -3, and I'm gonna have to subtract the charges of the ligands. So in this one, I would be subtracting -6 because each cyanide is contributing -1, and there are 6 of them. So that's a total of -6. And so what happens when you subtract a negative? It turns positive. So I end up doing -3 plus 6, and -3 plus 6 is a +3. So I can see that this is still Fe3 plus, but I had to do a little bit of math to get there because the complex ion was not 3 plus, it was 3- because of all the cyanides. The last one over here, I have a -2 or a 2- charge of oxidation state up there. This one, I only have 4. This one's going to be a tetrahedral one. I only have 4 ligands connected to my central metal ion. But what I want to pay attention to is that they're all Cl. Okay, and if you go look back up here at our list, Cl has a charge. It's a chloride ion. It's a -1. So because it has a -1 charge, I have to take that into account. And so I would have to use my overall charge, which is that -2, and then subtract, and then we're going to subtract -4 because each chloride is -1. And I can see that there are 4 of them up here in the drawing. So -2 minus -4 becomes -2 plus 4, which would be a +2. And that would mean that this central metal ion is copper 2 plus, Cu2 plus. So not too difficult, just a little bit of math on the ones if they're not neutral on all the ligands. And then when you guys, I would definitely encourage you, if you've not already watched the pre-recorded one of this, because the chart actually in the video actually looks different than this one. And it actually adds on their electron configuration or their orbital diagrams. And so it shows you a little bit better why they have so many different oxidation states. Okay, scandium doesn't. Scandium usually only has +3. And they show you why that is, because it has 4s2 and then 3d1. And so usually it will lose all 3. It'll lose the 4s2 and the one that's in 3d. So it usually only forms a +3. All of these other ones though, and there are some numbers in here that aren't even filled in, like nickel can actually be like 1, 2, 3, or 4. So there are some that are missing in here. And what you're going to notice is that as you increase, the number of possible oxidation states increases, and then at manganese, then it starts decreasing again. And then when you get over here to zinc, because zinc is technically not a transition metal by our definition, it only has +2 because it can only lose the 4s electrons. Its 3d is full with 10, and it's not going to lose any of them. And so what you're going to see is it's just kind of showing you based on their electron configurations or their orbital diagrams, what their possible oxidation states are, and kind of a little bit of an explanation why that is. And essentially, it's kind of what I said. It's because they can all be +2 because they can all lose the 4s electrons. But then the other ones will typically lose some of their d electrons as well. And that's what allows them to have multiple oxidation states. I can kind of compare a transition metal with a non-transition metal. So this one has calcium and chromium. And so if you notice, what happens to calcium is it's like 1, 2, and then all of a sudden there's a big jump here between 2 and 3. And we know that because that shows us calcium's ionization or charge is +2 because after its second ionization energy, there's a big jump. So that tells us that it has like, those 2 valence electrons that it's going to lose in 4s2. Whereas chromium has 4s1 and then 3d5. And so what happens to chromium is it's going to lose the 4s electrons, But then its next electrons in the 3D, they're all pretty close to each other. 4s and 3D, they're very close in the amount of energy. So there's not a noticeable difference between 4s and 3D. That's why it looks like it's just kind of gradually increasing there. But then all of a sudden, right here, between the 6th and the 7th electron that's lost, there's a huge jump. And that's because after losing these 6 electrons, the next thing that chromium has is 3p. And there's a huge energy difference between, you know, the 4s 3D and then 3p. Okay, for calcium, it came over here. This was the jump from 4s to 3p. For chromium, it didn't come till later because of the d electrons, allowing it to have multiple charges, unlike calcium. All right, so magnetism, definitely, again, highly recommend watching the one that's on Canvas because he shows you videos of compounds that contain each of these 4 ions, and he shows you the effect of the magnet, okay? When he shows you zinc, there's no effect. It doesn't attract or repel it. The reason it doesn't is because look here at its orbital diagram for the 3D sublevel. It's all full. There's no unpaired electrons, and that means that since there's no unpaired electrons, I underlined the wrong one. No unpaired electrons, that means it's diamagnetic, which means it's not affected by magnetic fields. Okay, it's not attracted or repelled. On the other hand, the other 3 that they show you, the copper, the nickel, and the manganese, they are all affected, but copper's the weakest, manganese is the strongest, nickel's kind of in the middle. And the reason is the number of unpaired electrons that they have in their D sublevel. Copper only has 1, so it is attracted, it's affected by that magnetic field, it's just very weak. Nickel's got 2, so it's affected a little bit more. And then manganese has 3, so that's the strongest effect. And so that's basically, this table is just kind of summarizing what the visuals of what he showed in the video with the magnet actually affecting copper, nickel, and manganese. And you could see that it affected it more as you went from copper to manganese, and then zinc not being affected at all. So because the other 3 that were affected, they have unpaired electrons, they're known as paramagnetic. So make sure that you can tell the difference between paramagnetic and diamagnetic. Diamagnetic means like zinc, no unpaired electrons, so you're not affected. Paramagnetic means you have unpaired electrons and you are affected by a magnetic field. And basically those bullets are summarizing what I just kind of said. All right. And then catalytic properties. This is our last thing today. I kind of talked about this briefly earlier at the beginning, but essentially catalysts, as we learned in topic 6 last year, catalysts are as a substance that provides an alternative reaction pathway with a lower activation energy. So basically it speeds up a reaction. It's going to make it go faster. Catalysts can be homogeneous or heterogeneous. Homogeneous meaning they're in the same state as everything else in the reaction. So if you have aqueous solutions and your catalyst is an aqueous solution, that would be homogeneous. If your products and reactants are all gases and your catalyst is a gas, that's homogeneous. Heterogeneous is different states. So maybe all your reactants and products are solutions, but your catalyst is a solid or a gas or something like that. So transition elements can actually act as both homogeneous and heterogeneous. Some examples that I mentioned a couple of them earlier, but there's this thing called the Haber process where they use iron to make a reaction go faster so they can create ammonia more quickly. Hydrogenation of margarine. So hydrogenation is a topic when we get to organic chemistry, we'll learn about hydrogenation. Essentially, hydrogenating something means you're adding a hydrogen atom to its molecule. And so they can actually speed that up by adding some nickel in to the reaction container, and that makes it go faster. And so hydrogenation of margarine, that's a pretty big industry because a lot of people buy margarine instead of butter, okay? Palladium and platinum in catalytic converters. So catalytic converters are things that they can put on cars to help them with their exhaust fumes. So like if your car doesn't pass inspection and it's an older car and it's giving off too much smog or too much pollution, they will put a catalytic converter that contains palladium and platinum in it, and that will help in order to reduce the amount of emissions that your car is giving off, and that'll allow it to pass inspection. So a lot of times if you have older cars, you might have a catalytic converter on your car to make it more environmentally friendly. Manganese dioxide in the decomposition of hydrogen peroxide. This is what, when you see those videos on the internet and they have like, you know, a container of something and then they add something to it and it explodes and it just like, it expands and it gets really big. It looks like foam. They're doing this reaction. They're taking hydrogen peroxide, which normally decomposes really, really slowly, like over months and years. And by putting some manganese dioxide and then also like some soap and food coloring for like the bubble, the foam effect, and the color, they're showing you this, and they're showing you the manganese dioxide speeds it up and it happens really, really quickly. Contact process is another industrial process similar to the Haber process, and in that one they would use vanadium pentoxide. And then these are the two that I kind of mentioned earlier, or I think I mentioned the one, the iron, where in your blood, your red blood cells, the hemoglobin, they need iron. They need iron ions. Specifically, I believe it's the iron 2 plus. If you do not have enough iron in your body, then your blood cannot transport oxygen as quickly. It can hold less oxygen, and so it's slower. And then you start to feel like tired, lethargic, or maybe like your fingertips and your lips kind of are blue because you're not getting enough oxygen to all of the extremities of your body. And so like, I know I have to take an iron supplement twice a day because I'm typically low in iron. Typically it happens to women more than men, but men can be have low iron too, but usually it's more in women. And so you can have anemia. Anemia is where you're low in iron, and when you're low in iron, they tell you that you either need to eat more foods that have iron or take an iron supplement during the day, so that your iron levels stay at a healthy amount and you're not having like, you're not being like tired and sick from not getting enough oxygen around to your different parts of your body. Another one is cobalt. So cobalt 3 plus combined with vitamin B12. This affects like the production of red blood cells, but also your nervous system functioning correctly. So, you know, your nerves, your brain sending all those impulses down the synapses. If you don't have enough cobalt ions, then the B12 in the cobalt will not allow those two things to happen properly. And so again, this is why when you go to like drugstores or like health food stores, they have like those whole sections where there's like bottles of like iron, cobalt, magnesium, manganese, zinc. Trying to think of other ones. Trying to think of what I take. I take iron. I take magnesium. I have a multivitamin that has zinc in it, and it has a bunch of other stuff in it too. I think it has chromium. But they have all these different metals, and most of them are transition metals because they are good for acting as catalysts for different things, different functions in our body. They all, you know, perform different roles. And so if you're low in any of them, then that could be why maybe like you're tired or you don't feel well or you have a poor immune system or something like that. And so that's why a lot of times doctors will be like, you know, when they do blood work, they look to see if your levels of all of these things are within the range that they're supposed to be, because if they're not, then they might recommend you taking a supplement or, you know, eating some vegetables or fruits or whatever that are going to have higher amounts of these things so that you can be healthier than you would be without them. Oops. No, I don't want to share screen.